tracking. And we were given test vectors by Lockheed Martin to start with 2D motion tracking, and these were test vectors we got. So basically the first test vector was just two balls going around in circles, and you're supposed to track it. So that's what we did. In the second test vector, it had balls disappearing for a while, and so we had to predict where the ball will be going while it's disappeared. So we added a prediction module which was able to predict the previous motion and analyze the prediction. And so that's what it does here. In the third motion vector, it was just a lot more balls, and they disappeared, and they were much more random motion. And so we were able to track that as well. And then the fourth one was totally chaotic, and they were merging, and they disappeared, and then they came back, and they went off the frame, and you were supposed to track it and predict where they were going. So to do this, we designed our modules, and this is our overview of the system design. So basically, we start off with noise filtering in the video, which we have techniques for doing, and then we use motion detection, which is a 3-step search, to narrow down the search region and generate blocks macro blocks where we think the motion is happening. And then once we have the macro blocks, we use object identification to narrow down the position of the block to make it into a center of mass kind of thing. So basically, if we detect this block, we'll create a center of mass and get the center of mass and just use that as a prediction vector. And then we use motion prediction algorithms to predict where the object has been, and then using that we analyze it and predict where it's going to be in the future by using equations of motion and such. And this was basically what Lockheed Martin required us to do, but we went ahead and we also did some camera integration so that we could do real-time video processing, and we also ported the code from MATLAB to in C# so that we could do it with FPGAs and do it in hardware. And that's what we came up with. So can you just walk by? So if we have motion nowadays, we can just track the motion in real time. We haven't integrated with predictions, so we can't predict that as of now, but we hope to do that in the future. So that's essentially a brief overview of what we've done. And this is a detailed explanation of the motion vectors. So
yeah, it'll grab. The basic idea is because what the TSS does is it uses a search region and neighboring block that you're trying to match. So what happens is that you have an object, maybe a 10-pixel block, and you look at a search region with maybe a 40-pixel block. And the idea is that the object is the same; it's just moving between frames. So it's just a ball; it's just the same ball. It's just going to be in a different place. So if the object moves too fast and it goes outside the search region, then you're going to have a problem finding it. So in this case, I think we used, if you translate, if you did it, what search region size did you use?
this right here?
50 pixels?
Yep.
Yeah. So then this 50 pixels, so you could say maybe about 1/8 of the frame it can jump before it runs off. So as long as it's moving less than 1/8 of the entire frame, either vertical or horizontal direction between consecutive frames, and you're all right.
Should be okay with more than that.
And I mean, obviously, by increasing the search region size, you can get better performance, but you also degrade the speed at which the algorithm runs by having more checks and bigger search region.
So this camera thing takes every motion?
Yes.
Or is there a limit of?
There's a limit of. You have a smaller limit so that if it's smaller than if the macro block is smaller than a particular size, it won't detect it. We decided to ignore it because then it was just detecting random motion and all. So we made sure that it was substantially moving. So.
Because one of the problems we had in these vectors that we got was you can see they're all black and white. And maybe, they're grayscale images. And so you have to actually extend these algorithms, especially the morphological filters, to work in RGB, which gets very complicated. And so what we did in this, we just used standard low-pass filter, and we said, okay, we're just going to assume it's easy white Gaussian, and we're just going to get rid of it. As opposed to hardcore noise like they have here. What's
the minimum size you ignored?
It's the block size.
So what? The block size you ignored. The threshold.
The threshold 15.
15? 1.5.
Yeah. So the error was less than 15 here. And it's a 4x4 block.